Hello, this is Jack Jackson. Now that we've taken a look at the ideas behind a z-interval, what it basically is, and basically how they're set up, and we derived a process for computing a z-interval and some formulas related to that, let's put those formulas and techniques to work to now actually constructing a z-interval. So we're going to do that on this example problem here. So for our exercise that we're going to look at, suppose that a standardized exam is to be given to a large group of probability and statistics 1 students. We want to compute a confidence interval for the true mean score of all the students taking the exam, but we want to do this, we don't want to actually just measure all of them, we want to maybe look at a sample and try to predict. So suppose that we know the standard deviation of all such test scores is 7. This last assumption is a little bit unrealistic, but later on we'll see what to do if we don't have this particular assumption. But for now, let's assume that we know the standard deviation of the population of all such test scores is 7. Now, let's suppose here that we go out and, well, what are we going to do? We're going to go out and make a representative sample. So maybe we randomly select certain students and have them take the test for us. And we use the sample data of scores to compute the confidence interval. So we choose a group of 20 random students, and they have these scores here. So what I'm going to do for you in this video is I'm going to step through this process of computing a z-interval step by step, and I'm going to ask you at every stage of the way here to actually perform the calculations yourself before we go on. So the first step is going to be, of course, to collect your data, and let's assume this has been done, and here it is. And then the next step is to compute the mean of this sample. So please do that. You should know how to do that, so please do that now. And when you're finished, come back to the video. So pause the video right now. Okay, well, how do we compute the mean? Well, we can either just add up those numbers and divide by the number they are. So add up all those numbers, divide by 20. Yeah, we could do it by hand. It'd be a lot easier with a calculator or a spreadsheet or something like that. Another way we could do it with our calculators is to put this data, say, into list 1 and then calculate one variable statistics, and as the very first thing that comes up, the mean is 75.1. So either way you do it, there's multiple ways, but they all boil down to just adding these numbers up and dividing by how many we have. And so that gives us our x bar, or our sample mean, 75.1. All right, so far what do we know? We know n is 20, that's the sample size. We know x bar is 75.1, that's the sample mean. And we know that the standard deviation of the individuals in the population, sigma sub x, is 7. Now the next thing we need to do is establish a desired level of confidence. Now this may be determined by standards for a research journal or some other such standards, something that's sort of kind of common in the particular industry you're working in. But in the homework problems, this will just be straight out given to you. So for here, let's assume that we're going to use a 92% confidence interval. So the desired level of confidence is 92%. So if 1 minus alpha is 92%, what is the confidence level of, and that should say 1 minus alpha over. Okay, so now it says the right thing. What is the corresponding level for 1 minus alpha over 2? Please compute that for me now. Press pause. Well, I'm going to show you two ways to do this. One is a step-by-step process here where we start with 1 minus alpha is 0.92. That means alpha is 1 minus 0.92, which is 0.08. Alpha over 2 is then half of that, which is 0.04. And then 1 minus alpha over 2 is 1 minus 0.04, which is 0.96. Or there's an alternative way that's probably, I would say probably a little bit easier. Notice that 1 minus alpha over 2 is 1 plus 1 minus alpha, and then divide by 2. In other words, you take 1 plus the confidence level and divide by 2. Or in other words, the 1 minus alpha over 2 is always halfway between the confidence level and 1. So we can do this as 1 plus 0.92 or 1.92 divided by 2 is 0.96 in this case. So either way you get 0.96. Do it either one of those two ways. Okay, so far what do we have? We have n equals 20, x bar equals 75.1, sigma of the x's is 7, 1 minus alpha is 0.92, and 1 minus alpha over 2 is 0.96. So the next step is that we need to compute the margin of error, E. So what is the general formula for computing E for a z interval? Now this formula is going to involve, does not involve x bar, but it does involve n, sigma, and 1 minus alpha over 2. So see if you can write down that formula now. Press pause. Well, hopefully you remembered it was this big red formula here in the middle, that the margin of error is sigma of x's divided by the square root of n times the inverse norm of 1 minus alpha over 2. Now you can just memorize that formula. It's a very important one. Perhaps if you're allowed notes, you could put that on your note card for a test or something. But if not, you may have to memorize that. You could possibly program it in your calculator or something. But it's probably useful to memorize it. Now it should actually make some sense to you, apart from the way we derived it earlier. But notice that the sigma of x is divided by square root of n is just the sigma of the x bars. So this is how many. This is one standard deviation of the x bars, and the inverse norm is a z-score. Okay, because this is from a z distribution or standard normal distribution. So this is a z-score which has a probability to the left of it of 1 minus alpha over 2. In your calculator, this might be also inverse norm of 1 minus alpha over 2, comma 0, comma 1. On the TI calculators, you can leave out the 0, 1 also, and we get this. This inverse norm of 1 minus alpha over 2 is sometimes known as z sub alpha over 2, because there's alpha over 2 is the probability to the right of that. So 1 minus alpha to over 2 is the probability to the left. So this is a z-score, how many standard deviations we are above the mean to get a probability to the left of it of 1 minus alpha over 2. And this is one standard deviation above the mean. So the E is the same distance as how many standard deviations above the mean you need to go to get 1 minus alpha over 2 as the probability to the left. But regardless, at some way or another, you need to know what this formula is. Okay, so now use this formula to compute the margin of error E. Just plug in the numbers that are above that apply, work it out in your calculator, get a decimal approximation. For now, just keep all the digits in your calculator. In fact, you might even take this and store the value you get as E. That way, if we use it again later, which we will, you won't have to type all those digits in again. Okay, so go ahead and try this yourself. Press pause now. Okay, so let's see, down here in the bottom right, you'll see what we have. Here's the formula again. E is sigma of x's divided by square root of n, inverse norm 1 minus alpha over 2. Up here in the upper right, you have all the values. So sigma of the x's was 7, so plug that in there. N was 20, so that goes in right there. And 1 minus alpha over 2 we saw was 0.96, that goes in the parentheses here. And then you just type this in your calculator, which you see I've done here on the left. So it's 7 divided by square root of 20 times inverse norm of 0.9601. Or you can leave off the 0,1 you see here, and you could do it. It gives you the same answer either way. And so we get E, and notice the last one I stored it as E, see there? And so we get E is 2.740257144. This is a TI-84 calculator, but TI Inspire calculator works exactly the same way. Okay, so here's what we have so far. N equals 20, x bar is 75.1, sigma of x is 7, 1 minus alpha is 0.92, 1 minus alpha over 2 is 0.96, and here's E, 2.74, etc. And we have this value stored as E in our calculator. Now, just finish up now and compute the confidence interval. For now, first do it and show all the digits that are displayed by your calculator, and then round off your final answer to 1 decimal place. Okay, go ahead and do this now. Press pause. Okay, hopefully you've been pressing pause and working through these on your own The whole point of this is for you to get some practice here. And here we go. The main thing we need here is just that x bar is 75.1 and e is this 2.74, etc. And so the confidence interval goes from x bar minus e to x bar plus e. So the interval goes from x bar minus e to x bar plus e. So you just plug that in, 75.1 minus e up to 75.1 plus e. And in my calculator, I'm just going to type in, I might store the 75.1 as m, that's the mean of the sample. So then I could just do this as m minus e to m plus e, and this is what I get. This is all the digits shown by my calculator, TI-84 calculator, and then round off to here, 77.4 and 77.8. Now, if you would, please go ahead and finish this problem by interpreting the answer in the context of the problem. Think about that. Come back when you're ready to check your answer. Press pause now. Well, look back at the original problem. Suppose that a standardized exam is to be given to a large group of probability and statistics 1 students. We want to compute a confidence interval for the true mean score of all the students taking the exam. Suppose that we know that the standard deviation of all such test scores is 7. First, we take a representative sample of scores and use it to compute a confidence interval. And the random group of 20 students were selected and given the exams, and this is their scores. State and interpret your answer in the context of the problem. Well, we would say a 92% confidence interval for the true mean score of all students is 77.4 to 77.8. So we are 92% confident that the true mean is in this interval. So remember, the true mean, however, is fixed. It's the intervals which are moving around if we were to repeat this with a new sample. So if we were to repeat this process with many samples of 20 scores, then approximately 92% of them would contain the true mean. Now, really, this last question really probably should have been done right at the beginning. So let's consider that. What assumptions were necessary to complete this exercise, and are they realistic? So it's really probably appropriate to do that first, because if the assumptions aren't met, then this process doesn't work. That's an important thing to think about in any kind of inferential statistics. There are different kinds of tests and techniques, but they all have some sort of hypotheses or some sort of assumptions. And if those assumptions are not valid or satisfied in that situation, then that technique doesn't apply. So what are they here? Well, if we think back, here are the things that we need. Look down here at the bottom. We're constructing a confidence interval for the mean of a population from a sample. We know the standard deviation of the population, and the distribution of sample means is normal, or at least nearly normal. So the question is, do we have those three conditions? Those are the three conditions in general needed for a z-interval to use this technique we used in this video. So the question is, do we have those three things satisfied? And then also kind of, are they realistic? Well, certainly we are constructing a confidence interval for the mean of a population for the sample. So certainly we have that. That's a realistic thing. We know the standard deviation of the population. We are told that the standard deviation of the population was 7, so yes, we do have that. However, this is a bit unrealistic. We'll see later what to do if we do not know the population standard deviation. Basically, what we'll do is we'll use the standard deviation from our sample in place of the population standard deviation, but then we have to slightly tweak the distribution a little bit. We'll talk more about that later on down the line. The final thing is the distribution of sample means is normal, or at least nearly normal. Now remember, if the sample size is greater than 30, we can assume that the distribution of sample means is approximated well enough to use these techniques regardless of the distribution. Okay? Now notice here that the sample size was only 20. So we need the distribution not to be just anything, but we need it to be somewhat near a normal distribution. Particularly, it needs to be free of outliers. It needs to be hopefully kind of mound-shaped in the middle. Especially, it doesn't need to be drastically skewed or have outliers. Those are the two things that will really mess it up. So one way we could check this is with the normal probability plot that we had studied earlier in the course. Now, since I entered the data into L1 on my TI-84, we can use the calculator to produce a normal probability plot. Okay, and the way you do that is you do second y equals will be a stat plot, and then you go to plot 1 and turn it on. Make sure you choose this last one here. The data is in list 1, and mark it with the some mark here. And then I did a zoom fit. I turned off my other graphs, and then I did a zoom 9, and we get the probability plot, normal probability plot. And if it's normal individuals, this should be close to a straight line, and it's fairly close to a straight line here. So we see that certainly this is close enough that with a sample of size 20, we're pretty confident that the distribution of sample means is close enough to normal to make the results valid. Okay? So there's a good example of computing a z-interval. We'll put this into more practice in another example in the next video.